Okay, we're good to go.
Well, dear people, thank you for attending the second seminar of the European Tensor Network. It's a great honor to welcome our speaker, Bruno Nachtergaele from UC Davis. Bruno is a fellow Belgian, did a PhD with André Verbeure in Leuven, and went on to become one of the world experts on the mathematical aspects of quantum spin chains. His paper called Finitely Correlated States from 1992, co-authored with Mark Vannes and Reinhard Werner, is a must-read for anybody in the community of tensor networks, and anticipated almost all theoretical developments in it. I have been trying to finish it, but even after 20 years, I still did not manage to absorb all subtleties and beauty in it. Today, Bruno will talk about tensor networks and low complexity eigenstates of many body Hamiltonians. There will be plenty of time for questions after the talk. Please, Bruno, the stage is all yours.
Thank you, Frank, and thank you, the other Frank and Norbert, for organizing this seminar and giving me a chance to talk. So I understand you're all relaxing at the end of the day, and I'm impressed that your choice of activity would be to listen to a talk about mostly mathematical aspects of tensor networks. So what I will do is say a few things about the origin of matrix product states and tensor networks, and then talk about some recent work, in particular work that is joined with Amanda Young and Simone Warzel, who are in Munich. And I think it's kind of quite interesting application of matrix product states and a slight extension of them. Okay. So here's my outline. So the early history of tensor networks is a history of acronyms, you could say. So I will sort of quickly go through this list, and it's not a complete list of acronyms, and it goes on, but this is sort of the early stuff that I know. There's AKLT and DBS and QMS and FCS and MPS and PEPS and TNS. I will not explain the acronym TNS in this seminar. I'll make a few remarks about that, where things come from, what people were trying to do. And then I will talk about two recent results that have to do with the spectral gap primarily in two models. So things that were proved last year and this year. One is the AKLT model in hexagonal lattice, a classic thing that was already mentioned, and the gap was conjectured in the original paper by Affleck, Kennedy, and Tasaki. There you go, AKLT, first acronym. And then the other model is a pseudopotential model introduced by Haldane, adapted, truncated, for the fractional quantum Hall effect that you see in lowest Landau level at 1/3 filling, and explain that briefly where it comes from and what we did for that model. And so we studied the ground states of that model, and this decided we could describe it as what I would call fragmented MPS states. I'm going to explain what it is. It's very simple. And it turns out that the same picture that allowed us to study the ground state and the spectral gap for this model also allows you to study excited states. And they are of particularly low complexity, and there's some interesting questions related to that. And so it's something worth discussing. Okay. So AKLT models. That's really the origin of matrix product states and tensor network states. And of course, nothing starts from totally out of the blue. The models were introduced, and the analysis was done to actually show that the conjecture phase, the Haldane phase that Haldane predicted, would describe the ground state of the spin 1 antiferromagnetic chain is in fact realized in a model, and you can prove that you have the predicted properties of a unique disordered ground state, exponential decay correlations, and a gap above the ground state. So the AKLT chain, the simplest example of AKLT models, did exactly that. And they found a Hamiltonian for which they could construct the exact ground state, and they call it a valence bond solid state. And already in its name, it sort of shows you that it's a particularly simple structure that they use to prove the properties. And then also they find a much more general class of models on arbitrary lattices, trees. Things were generalized even further. But sort of as a practical definition of what I consider is the standard AKLT model, I would say, you can define it on a general graph. You have a spin, finite dimensional Hilbert space for a spin at each vertex. The dimension is the degree of the vertex plus 1. It's the dimension of as many spin 1/2 as the degree of the vertex. And so this is an SU2 invariant model. Already in the original paper, AKLT explained how you have SUN invariant models and why it might be interesting to study them. And this was picked up by other people and extended. There's an important paper by Arovas, Auerbach, and Haldane, for instance. The general model on graphs was studied by Kirillov and Korepin. And I would say sort of the standard AKLT model, what I mean by it is the following. You have this, this spin of dimension dx, degree of x plus 1. And then you have an interaction at each edge that projects on the highest spin space of the pair of vertices that make up the edge. And if you trace this back to what I see here, this projection should be on total spin, the number z over 2, where z is the sum of the 2 degrees of the vertices that make the edge. So that's the standard AKLT model. For instance, I know you all know it. I don't have to write it down. The standard AKLT chain, the spin 1 chain, there's a projection on the spin 2 states for a nearest neighbor pair, and that is the AKLT Hamiltonian. Okay, so here is the paper. There was a PRL in '87, and then a CMP paper in '88. This was before the archive was widely used, and so it took a while for me to become aware of these papers, and this will be relevant, and you will see in a second. And these are actually figures taken from the original paper by AKLT. And as you see, they look very much like we think about VBS states and tensor networks, in fact. So you see the pair of spin 1/2 that are projected onto spin 1. So you can represent it with a tensor. The spin leg is not drawn here in this picture. This is the VBS picture. And even the product structure was more or less understood already in this paper. If you want to sort of glue together 2 pieces of a finite chain, then you have to contract these pairs of indices. That is the projection onto the spin 3 states. And I will say a little bit more about this, this model in a little bit. Okay, I got a message that my internet is unstable. I hope this will just be a temporary problem. So something I was thinking about around that time, I was finishing my PhD in Leuven, and we had a school in quantum probability, and Luigi Accardi was there, and he talked about quantum Markov chains, which is one of the sections here in his paper, Topics in Quantum Probability. And I thought it was kind of interesting, and for various reasons I was interested in that. I mean, we don't have to go into this. There was also a paper by Accardi and Frigerio a couple of years later that used this concept of quantum Markov chain to define a set of states for quantum spin chains. And so I was thinking about that, you know, what we could do with this and what it meant and what the structure was. And in fact, I gave a talk at a quantum probability conference in September '88. That was before we'd actually become aware of AKLT work, and certainly we had not absorbed it or understood it. But I had been thinking with Mark Farnes about trying to apply these states to spin chains, and in fact we used it in sort of variational calculation for the antiferromagnetic Heisenberg chain, and well, it captured the short-range correlations, and the energy wasn't too bad, but also not too great. And we asked in this paper, there's not too much interesting in this paper, we hadn't really gotten anywhere. We asked whether perhaps there would be models where the exact ground states are described by these kind of states. But we didn't know the answer. And then early the next year, I moved to Chile. We still hadn't resolved this. But I continue to think about that. And Mark, in fact, early 1989, visited Dublin. Probably had some project in mind. I don't remember what it was. So he was visiting Reinhard Werner, who was in Dublin at the Institute for Advanced Study on some fancy German fellowship. If I remember correctly, I don't remember exactly which. But they started talking, and so sort of independently, we finally figured out that the ground state of the AKLT model can be fit into this concept of Accardi's quantum Markov chains if you tweak it a little bit. Then with Reinhard Werner on board, the thing, he gave it a huge push. He immediately realized the whole family of states that could be just constructed out of SU2 representations, and you could do exact calculations and things like that. And this looked really interesting. And so we had to generalize sort of VBS and quantum Markov states and fit them into sort of a framework that covered all of them, and we called those finitely correlated states. So that's the other acronym, finitely correlated states. And there's a special subclass of those, which we call purely generated, which are now called matrix product states. So that's where they first appeared, and then we had a paper later that year in Europhysics Letters, and then wrote a long paper, the paper Frank referred to. So I was very disappointed to hear he has not yet finished it, reading it, but well, maybe it could have been better written. You know, with hindsight, I can certainly say that it could have been better written, but I still like it. It's a nice paper. And it took a little while to get it published. It appeared in '92. But here are two formulas. Actually, these are formulas I copied from the Europhysics Letters in '89. So there is sort of two things. So this transfer matrix structure was what Accardi had in mind, and it's totally present in the finitely correlated state. So here is, you can express correlations by using the transfer matrix, E hat, we called it. And if you look at the purely generated case, the matrix product states, and you write them in a basis, what you find is that the coefficients are indeed given in this form. So this is a tensor product basis for the chain, and then labeled by the basis elements, you have matrices, and the expansion coefficients are trace of the product of matrices times some other matrix, which gives you some freedom. You generate a finite dimensional space of vectors, and these are the matrix product states. So we thought this was interesting, and we analyzed this, and I think one of the nice results we got in this paper that we have sort of a general proof for in one dimension that these states are ground states of gapped Hamiltonians. So you can prove there's a Hamiltonian. These are exactly the ground states, and it has a spectral gap. So we explored a number of things. We hadn't So originally we tried to use these kind of states in variational calculations. So it's one of the things we looked at, how many of these states do you have? And indeed, it's a weakly dense subspace of states. So in principle, you can approximate the energy of any one-dimensional model with finite range interactions arbitrarily well, and things like that. And in fact, a little bit later, around the time the paper came out, I think, Steve White's DMRG appeared, and he had been thinking about MPS for a while. But then it was clear to us that the fixed points of this algorithm, when we saw it, would be indeed MPS. And we thought that this was an interesting connection, but we were all doing other things already by that time. And so it was a nice paper by Östlund and Romer that makes that explicit. And nowadays, of course, everybody understands the connection between DMRG in one dimension and matrix product states. So in the years after, there were more spin chains were found by many authors. And I don't want to sort of diminish this, but in fact, things were relatively calm for 10 years. The AKLT paper, for instance, already anticipated that you have also these models in higher dimensions, right? Like the hexagonal lattice, in which you have a PEPS ground state. But there wasn't really all that much progress. I think Reinhardt had a student working on it, had a master thesis. And so the high dimensional case, we didn't really get very far. And so, relatively speaking, it was sort of quite quiet for 10 years until Frank Verstraete burst on the scene. I think that's the right way to say it. And of course, with a lot of able collaborators. And I mentioned a few names here. And I know this is, it's sort of what I remember. And there's many more people involved, and many more people have done interesting work. But I don't really know that much about the current history of TNS and how it has exploded in a big field and proved useful for many, many different problems. But sort of in my memory, it was really Frank who sort of made the connection and made it visible, and reminded people of that paper on finitely correlated states. I think that was very nice. Okay, so that is history. I don't know whether there are questions about this. I mean, maybe this is more suitable for an offline discussion. So maybe I'll proceed and talk about the recent results that I would like to present that we obtained in the last 2.5 years or so. But if there are any questions right now, I'd be happy to answer them. All right, well, Frank will tell me if there's a question. So very good. So my first topic is about the AKLT model on the hexagonal lattice. So it's a model that was introduced in the original AKLT paper, so it's old stuff. And as I said, so it's spin 3/2, so a 4-dimensional Hilbert space at each side, and has the standard AKLT Hamiltonian projection on the spin 3 states for each edge. And in the 1988 paper, AKLT conjectured that this model is gapped. So by the way, they also proved that there is a gap for the one-dimensional AKLT model and some other models, Majumdar-Ghosh and some other models. But in 2 dimensions, they couldn't prove that there was a gap, but they conjectured that there was one. And so a gap means, of course, a gap above the ground state, which is 0 for all these models. They're frustration-free, uniform in the volume. And they had good evidence for that. They actually wrote a paper. So they have a discussion of the exponential decay of correlations of this model in the CMP paper. But then they wrote another paper where they have a more elaborate analysis where they prove that there is exponential decay of correlations for a very large class of boundary conditions. Because you could be worried if you pick one particular boundary conditions, you are sort of have a disordered phase, maybe with other boundary conditions. you have long-range order. Maybe there's some symmetry breaking that prevents exponential decay to occur, but not in this model. It's not the fully general boundary condition, but it's a pretty large class. Basically, you can fix spins arbitrarily on the boundary. But that was 1988, and I thought about it off and on, and I'm sure many other people have. You know, how to prove this, or how to prove, in fact, that for any two-dimensional SU2 invariant spin model, short-range interactions, that you have this kind of disordered ground state and a gap above it, right? So there was not a single example until last year where you could mathematically prove this. And we had a workshop that was in the fall of 2018. Robert Sims, Hussam Abdul Rahman, and Amanda Young organized a workshop in Tucson, where we would talk about, among other things, spectral gap problems. And we spent a whole day essentially talking about the AKLT model and the hexagonal lattice and why everything that you try just fails and things like that. So while this didn't really solve the problem, it did lead us to think that everything we wanted to do would actually work if we added decoration to the hexagonal lattice. And so by decoration, I mean, so in a regular way, add spin 1 variables, add additional vertices with each with a spin 1 variable. So that is what you should do if you wanted to construct the standard AKLT model on this new graph with additional vertices, because these are degree 2, so they have spin 1. And then you do the corresponding projections for the interactions. Then everything actually worked out pretty nicely. And we proved the theorem that appeared a year later with a number of participants of that workshop. That's Sam Abdul Rahman, Marius Lam, Angelo Lucia, and Amanda Young. We proved that if you decorate with n equal 3 or more, so this picture is for what we call two decorated lattice. So there's 2 additional vertices for each edge. So if you put at least 3, then in fact we can prove the corresponding model has a positive gap uniform in the volume. Okay, so you can be positive and say here is an SU2 invariant model, 2 dimensions, and you can prove there is a gap. Great. Or you can say, well, this wasn't the original model, right? And both are true. So, but it set people thinking, and maybe we can do more, maybe we can do better. And in fact, it's kind of interesting. There was sort of a quick history. So through the course of last year, we got to the point where we essentially have a numerically assisted proof, or 2 numerically assisted proofs for the spectral gap for the AKLT model on the standard hexagonal lattice, so without these decorations. So after 30 years of apparently no progress, which Leap reminded me actually from time to time, how is this possible that you guys are not making progress, right? Well, finally, things started moving. So our paper was put on the archive in January. And then Marius Lam found some able numerical collaborators in Boston, Anders Sandvik and a younger person, Yang. So where they proved for not a 2-dimensional model, but just a sequence of hexagons, a necklace of hexagons. I don't have a picture here, but I guess you can imagine it. Just hexagons kissing each other, edge to edge. And he used finite size criterion, Knabe, plus DMRG to do the calculation that you need to do. You need to prove that the gap is sufficiently large for some finite system to use that criterion, and they proved that this was a gapped system. Or maybe this is not too impressive because sort of this is really a 1-dimensional system. A little bit fancier than just a simple chain, but it's a 1-dimensional system. And then the next month, Pomata and Wei came with another paper, and they considered AKLT models on other decorated lattices, in particular square lattices with additional vertices on the edges. But in fact, people have considered all kinds of lattices. You can be creative, and they used sort of the method that we used to prove the theorem is really the original argument that we have in this paper with Vannes and Werner, and you can get for the decorated hexagonal lattice, you can get an analytic proof. And well, for the square lattice, the analytic calculations you need to do, and maybe I will show you in a minute, why they are easier in one case than another. But with some exact diagonalization, you could actually make this work and prove that these models were also gapped. But these were decorated models. That's not really the standard hexagonal lattice that we really wanted to know about. But Lem and Sandvik and another collaborator, Wang, pushed forward with Knabe's finite size criterion, which Lem had worked on. There's some variations. You can sort of fine tune it. You can add in parameters and be more sophisticated, and you can get it close to work in 2 dimensions. And in fact, they succeeded to do DMRG for a sufficiently large patch of the 2-dimensional hexagonal lattice. I think it has 7 hexagons, if I remember correctly. 36 spins. It's pretty large, but they're very confident that that's good DMRG, and I have no judgment about it. And so you need to make sure that a finite system like that, with specific choices of the coupling constants and so on, has a gap that is sufficiently large so that the argument works, but they made it work, and they got a, what I would say, numerically assisted proof of the gap for the hexagonal lattice. And barely a couple of weeks later, Pomata and Wei also came with a paper where they actually considered the same model, but they used the method using small commutator estimates for projections on ground state spaces and exact diagonalization to compute the norm of such a thing and to prove that indeed the AKLT model in hexagonal lattice has a gap. I'm sort of partial to this second approach, in particular because the numerics is just basically calculating an extreme eigenvalue for some relatively small system, and it was not that big. It's smaller than what you needed to do for the Knabe criterion, so I kind of liked it better. But anyway, so 30 years after the conjecture, we have almost a proof. It's not entirely analytical, but it has, with the assistance of numerical arguments, now we know that this is a gapped model. Okay, so we did it analytically, and we needed to add 3 sites at every edge to make it work, and I can sort of explain you why that is. If you want to do numerics, actually it's enough to add 2, but we couldn't do that analytically. And we did it by comparing the Hamiltonian to so everybody sort of who knows a little bit about these AKLT models and other frustration-free models, if you are studying the gap, you can replace your projections by projections on different subvolumes, and they are related by a simple constant. And so instead of instead of edges, you look at this Y shape as the fundamental volume. You can write a Hamiltonian up to multiplicative constant with this projection on the complement, the orthogonal complement of the ground states of the model on this kind of shape. And then what Vannes and Werner and myself did, we used a lemma about projections. I'm not going to go through the mathematics. It's too late in the evening for you guys. Most of you, I understand, are enjoying this as entertainment. So let me not go into the mathematics, but you have to estimate the commutator of 2 projections on 2 y's that overlap in a lag. So there's overlap, right? They don't commute, but the commutator is not too large. And if you can do that, you can prove a gap. And so basically you have to analyze a system that is the union of 2 y's like this, and you can see it's more or less one-dimensional, and it's understandable that you can use analytic techniques to get what you want. but you make use of the additional, so these are short AKLT chains which have good decay of correlations, and that helps you out to prove the estimates that you want. Okay, so that is sort of a nice thing that happened last year, I think. I don't know why it had to take that long, but at least we know for this, and we can envision how to prove for other two-dimensional models with these disordered ground states that they are in fact capped. Okay. So the other new result I wanted to talk about is also about a spectral gap. It's in a sense also about a two-dimensional system, although it appears in the end in the form of a one-dimensional Hamiltonian. So, but it's kind of interesting. I think it's interesting for two reasons. For what we find, and also it's a model that people have used to try to understand the fractional quantum Hall effect, say in the 1/3 filled lowest Landau level. So, well, everybody knows, but let me just give sort of a quick background, so where the model fits and where it comes from. So it's about the electrons in 2 dimensions in a perpendicular magnetic field. If you have no interactions and just have one electron, or if you have no interactions between the electrons, then you can describe the spectrum by exactly solving the magnetic Hamiltonian. You get Landau levels, which are infinitely degenerate states separated by a constant gap. And so what the physical intuition was that if you fill a Landau level at a fraction, say 1/3, then in fact the interactions that are of course there between the electrons will generate a gap, and that is an essential ingredient in the explanation of the fractional quantum Hall effect. So, okay, I'm not going to give any details. Let me just sort of repeat what I just said. Well, we're going to work in cylinder geometry. That doesn't affect the picture very much. Of course, it changes the exact form of the eigenstates. So you take periodic boundary conditions, say in the y direction, and you take open boundary conditions in the x direction, compute the orbitals that span the lowest Landau level. There's some nice formulas you can give. I'm not writing them here. But they're basically exponentially Gaussian localized orbitals in the x direction, and they have some oscillating structure in the y direction. And the characteristic sort of separation of these, the centers of these orbitals is L squared over R. And so they will be well separated if R with respect to L is small. So this is going to be a model that is physically well justified if R is not too large. But in principle, we have not made any approximations here. We have not introduced an explicit Hamiltonian. So little L is the magnetic length is related to the magnetic field. Okay, so Laughlin, of course, proposed this famous wave function, but it's just a ground state wave function. And if you want to show there's a gap, you actually have to have some model Hamiltonian to look at. And so Haldane and other people computed an effective Hamiltonian projected to the lowest Landau level that would describe the short-range repulsive interactions between electrons, electrostatic interactions. And if you are in this thin cylinder regime, so what you get, you can label the orbitals of one integer. So you get a one-dimensional model. There's other ways of doing it, but if you have this one-dimensional model, then you have, in fact, you have interactions of arbitrarily long range, but in this thin cylinder geometry, the strength of the interactions decays very fast with the distance. And so it seems reasonable to truncate and throw away the terms beyond a certain point. You keep only basically 2 terms. And this is the Hamiltonian you come up with. So you can think of this as spinless fermions in one dimension, or equivalently spins. It really doesn't make a difference. So the C's are either creation-annihilation operators for fermions, or they are Pauli raising and lowering operators. Hamiltonian takes the same form, everything is exactly the same. If you think about spins, you don't have to worry about signs, it's kind of better. So there is a term that is expressed in terms of numerator, so there's electrostatic repulsion for if two orbitals at distance 2 are occupied. And then there is a term that has some other electrostatic contribution and also hopping, but it's not the sort of traditional hopping. It's what is sometimes called dipole preserving hopping. You hop in pairs, right? So the term in Hamiltonian is Q star XQX, shifted then throughout the one-dimensional lattice. And this QX is these two terms. So it interchanges two occupied sides, say that are nearest neighbors, say it's x is equal to 0, and 1 and 2, with where the two particles occupy 0 and 3. So they do this hopping. It's there in 0 and 3, or 1 and 2, 0 and 3, 1 and 2. But they do this in unison because you have the two hoppings together there. You could also say that center of mass is conserved by these hoppings. And there are some important consequences. And a very nice thing that was, I think, discovered by these people here, Lee and Lenas and Bergholz and Correlated, is that this is a nice frustration-free Hamiltonian for which you can study the ground states exactly. And so that's a good starting point for us to try to think about the spectral gap. Here, there is some physical way that the two coupling counts. So there's a lambda here, which is the amplitude, sort of the hopping if you want, but there's an overall kappa, non-negative constant here. If you really calculate them from the original model, the electrons, the magnetic field, repulsive interaction, they are related in a certain way in terms of this, and given in terms of this parameter alpha, which we have to take relatively large to justify that we have forgotten all the longer range terms. So the longer range terms are even smaller coupling constants. Okay, so that's the model. Translation invariant, as I say, preserves particle number, but not only particle number, also center of mass. And you can actually play a little bit with these symmetries and figure out that any ground state would have to be at least threefold degenerate. It's a simple argument put in the paper. And as I said, there's other interests. It's not just a fractional quantum Hall effect, but this kind of interesting behavior that we found and other people found in this Hamiltonian, and interesting to read about. And I will maybe just briefly come back at the end when we talk about excited states. But for now, I'm going to study the ground state space and state the result that we have about the spectral gap, exponential decay of correlations, and then a few things about the excited states. I'm not going to do anything too technical. All right, so here is a Hamiltonian again. And let's think about it as a spin system. It's kind of simpler. Everything is tensor products, and it's entirely equivalent. So as I said, this Hamiltonian is frustration-free, and I will show you some ground states in a second. And in fact, we construct the full ground state space, and it turns out it's actually quite large. It has the dimension of the kernel for a finite chain grows exponentially in the length of the chain, and you can asymptotically figure out exactly what the exponential growth is. It's about this. And you can also see from the construction that actually 1/3 is the maximal filling, at least asymptotically. You can have a particle number at most equal to 1/3 of the length of the chain, right? And these are the states that show the behavior you expect in the fractional quantum Hall effect and the excitations above the ground states. And sort of a good way to start is to look at the limit where you only have the electrostatic term, lambda equals 0. And if you look at that, and then so there is no hopping. There is just this term, and then Q star XQX is just another electrostatic repulsion. So nearest neighbor particles pay a price, positive energy kappa. Next nearest neighbor particles pay a price. It's normalized to 1 here. So the most you can do, the closest you can pack your particles in this Hamiltonian, is every third side you can put a particle, right? So the 1 signifies occupied orbital, then there's 2 empty ones, occupied, 2 empty ones, and so on. It's called a Titleist state. They actually introduced it and sort of explained the basic physics of fractional quantum Hall effect based on that. But the interesting thing is that you can find exact ground states for lambda different from 0 by starting letting the electrons hop according to this hopping term. And so what that means is that if you have 2 particles at distance 3, like for instance, take k equals 0 here, so it's start 1 and 4, you can interchange them with occupying 2 and 3, 2 nearest neighbors, right? So that's exactly what this hopping term does. And if you take the product of all these hopping operators, you will get a superposition of many particle configurations. And there's a simple description that I will detail a little more in a second. And it turns out, in fact, that this is an exact ground state of the Hamiltonian at non-zero lambda. This is called the squeezed tau state. You could say it's resonating tau state. The particles are hopping back and forth. And these states play an important role, so I gave them a separate notation. So this works, of course, perfectly well if you take an interval of length, a multiple of 3, 3n, and then we call them phi n, right? So these are exactly these states as defined here. And it turns out they're matrix product states. Bond dimension 2. And since I broke the translation symmetry to introduce this state, it's clear that there's going to be at least 3 of them, right? Okay. So let me sort of repeat what I just said. We can label one of the 3 state, these Titleist states, by sort of repeating the pattern 1, 0, 0. And we can construct from this pattern an exact ground state for lambda different from 0 by taking an equal superposition of what you can obtain by letting these particles hops in pairs. So we call these monomers. And here we have a dimer. And so these 2 have to be in superposition to get a ground state. But then also, these 2 monomers have to be resonating with the dimer here, where these 2 have jumped in the dipole fashion. And these are the only things you can do. And you take them with a weight. So there is a weight lambda here, and a weight 1, and that will give you exactly this state, and it will be the exact ground state of this model. Okay. So, but now if you want to study the gap, we have to, of course, the way what we were thinking of doing, you need to know the complete set of ground states, and you have to have enough control of them so that you can actually compute. So these we called VMD states, void monomer dimer states, because it turns out that it was already clear in the electrostatic picture. If you have some more voids, you have fewer particles, then you can also separate them enough so that there is no electrostatic energy. And it turns out that all such patterns can be turned into an exact eigenstate of the Hamiltonian by doing the substitution between pairs of successive monomers and dimers. And so the big difference is that you can put voids in between the monomers. There's one here, there's one here, there could be more. And then there's boundaries. You may have to consider chains of length that isn't a multiple of 3, or where the pattern that you put with your monomers doesn't exactly fit with the finite size of the boundary. So you need to introduce some boundary tiles as well. And you can figure out exactly what it is. And so on the left, you can put this. On the right, you have a choice. You make arbitrary configurations like this. Then you make a superposition by letting these resonate, whenever you see two monomers, you can replace it by a dimer multiplied by a factor of lambda, sum over all possibilities, and you get a vector that is labeled by this tiling here without dimers, so we call the root configuration. And then it turns out we have a nice theorem that in fact, all these states thus constructed, labeled by these root tilings, are an orthogonal basis of the kernel of the Hamiltonian Westmont. Oh, that's good. Not only it's a spanning set, it's actually an orthogonal basis. I mean, they are normalized. You can compute normalization factor if you want. The important fact is that they are an orthogonal basis. And then from this tiling picture, I mean, now you can count, of course, you just have to count to find the dimension. You can see there's some combinatorics problem. It's not too hard. You get recursion relations. You can analyze it, and you find this exponential increase. You can also see that there's no way of packing more particles than roughly the length of the chain divided by 3. Due to these boundaries, you can add a few more, but asymptotically, it's 1/3 filling. And if you think how these substitutions work and what the role of the voids is, then you see that in fact, you get a very simple structure in these states. You have a tensor product structure. So if there is no voids, you have these squeezed tau-tau states. And then what happens if there is a void, and it sort of breaks the chain into pieces and the state factors. So you can have a piece of tau-tau state to the left, to the right. And then at the end, you can have some other thing that deviates, and you can classify exactly what you can have there. But that is the general structure of these states that form an orthogonal basis of the ground state space. And they all have Schmidt rank less than 2. They're very simple. But they're not just one matrix product states or two matrix product states. So we call them fragmented matrix product states. And because of the combinatorics of this fragmentation, there's an exponentially large number of them. Okay, so we can prove that there is a uniform gap for this model. If lambda is different from 0, well, lambda is equal to 0, yeah, there's electrostatic Hamiltonian. It's gap 2. You can, depending on whether kappa is greater than 1 or smaller than 1, kappa is the gap or 1 is the gap. But for lambda different from 0, we have the following lower bound. Now, first there's a prefactor that is the gap for some finite chain. And in fact, you have to consider 3 lengths, 8, 9, and 10, as it happens, for the way you did it. And then there is a factor of this kind, 1 minus some positive quantity that is given in terms of a function, which I'm not going to give you the formula, but it's an explicitly defined function. It's the maximum of a sequence of functions that you can explicitly define. You can definitely calculate and make a graph of, and here is the graph of this function. And so this, when this function is strictly less than 1/3, is a positive constant. We have a positive lower bound. And this happens to be the case for quite a large range of the absolute value of lambda. It includes, in fact, the total, the physics, what people say in the original model is the physical range, which is lambda between 0 and 3. So you can plot it, and you can see it's somewhere 1/3 is attained somewhere here. It's a monotone function. It's somewhere around 5.35 or something like this. And this theorem we prove using a martingale method, and people who are familiar with that will know, I mean, it's essential to understand, well, I would say always in these kind of models, intersection property of ground state spaces, which now have these large dimensions. So it's a little bit of work to do this. Amanda and Simone did a lot of the work. You have to do a lot of counting, be careful. But you have an exact intersection property, as you have for the AKLT model and the models with a standard single MPS ground state. We can also give you a similar estimate for periodic boundary conditions. But there is a problem, and which is that the gap estimate vanishes as lambda goes to 0. Now, for lambda equal to 0, we have a gap. It's either 1 or kappa. And so it's positive. But if you look at the numerics, because here you have the gap of these finite chains with open boundary conditions, the one we had to use to have this nice construction. So here on the left, I've plotted the eigenvalues for a finite chain of length 12 in this case, but it doesn't look very different for other finite lengths. And what you see is that there is eigenvalues that vanish in the limit lambda going to 0. While if you do periodic boundary conditions, you don't have that. And so the bulk gap is really not expected to vanish as lambda goes to 0, but we haven't really found a way around that. So for every non-zero lambda, we have a lower bound for the gap, but its behavior is not really good if you compare to what's expected for the bulk gap for small lambda. So this is a spin chain of length 12 with lots of eigenvalues. And this looks like a pretty sparse plot. And in fact, I think, if I remember correctly, I plotted 2,000 eigenvalues here, but you don't see 2,000 lines. And the reason is that all of these eigenvalues have a large degeneracy, that, as far as I can tell, all that grows with the volume. And so this is kind of a sparse spectrum that you have. And this is related to the structure of the eigenstates. Not that much time left, maybe, but I can explain a little bit. I chose a particular value of kappa. This is not important, but here, this is the sort of how the spectrum looks. And I've also drawn here a red curve, and I will talk about it in a second. So we think we have identified indeed the first excited state that you should have in the bulk. It's not the first excited state due to boundary conditions. We also have actually exact eigenstates that show this behavior for finite chains with open boundary conditions, where the energy vanishes quadratically in lambda as lambda goes to 0. But we also have upper and lower bounds, in fact, for this first excited state that make us think that sort of we know in principle what the first excited state is. The estimate, of course, is if you take into account constants and things like that, is not that good. I mean, it's right order of magnitude, but it's not close. But it's a theorem. That's worth something. Okay, so so one of these ground states was a matrix product state, I said, and this was known before. And of course, people know what to do with matrix product states. So this maximally filled squeezed Titleist state is a matrix product state. You can compute correlations, and there's all various correlations and string order and things like that have been computed by these people, by Bergholz in particular, but also in this paper with Nakamura and Wang. And the exponential decay was also computed by Sabine Janssen. And you can get the exact expression for the correlation length. If you know about matrix product state, of course, it's not a surprise. So here it is as a function of lambda. But now we know that there is many more ground states, and we also know there is a spectral gap. But this is kind of maybe a good place to remind ourselves that if you have this large degeneracy of the ground state space, there is no theorem that tells you that a spectral gap implies finite correlation length. So you have to do something explicit. And indeed, I mean, it's not a surprise, given the structure that I explained, this fragmented matrix product structure still allows you to estimate the correlation length. And in fact, you get a similar expression for the exponential decay between arbitrary observables with the same coefficient C lambda here, while there is a 1/2 due to the fact we estimate we lose a 1/2. That probably shouldn't be there, but we did lose it. So that is the estimate. And this is not just a sort of mathematical nicety. We don't have this theorem, so we don't know that a gap implies finite correlation length, but of course we know it always does. No, it doesn't. You can, in this large space of ground states, easily construct examples, pure states, nice states, that have arbitrarily slow decay of correlations. Arbitrarily slow power law, no exponential decay. So what is special is that we have a specific orthogonal basis of the ground state space, all consisting of very simple states that all have exponential decay of correlations. And of course, you're happier to work with those. So this is, I think, an interesting pointer to perhaps what is true for this model, also for the excited states. And okay, I don't have complete results about that, but I'm happy to make some comments about it, and that's what I want to do in this slide. So, but clearly these fragmented MPS states, like I repeat here, so if you ignore the boundary, it's really just an MPS state, and then maybe maybe 1 0 or a couple of zeros, some vacancies, there's a void, then there's another MPS state, and so on. So that obviously are states of finite Schmidt rank. They're very low complexity, and so you have a whole basis of the ground state space with states like that. But it's interesting that in fact the excitations built on that, and maybe you can expect this, but it's sort of nice to try to verify this. The excitations built on these ground states are also low complexity. And for instance, what is expected to be the lowest excited state, and it's been called the magnetoroton, and it's a particle hole type excitation that people have studied also numerically. You can find such a state in the invariant subspace they obtained. It's called Krylov spaces, right? You take a vector that you're sort of inspired by this picture of constructing from a root tiling in a ground state. Now you make a mistake in your root tiling. Instead of the dimer we should have here, the monomer we should have here, 1 0 0, I put 0 1 0, right? So I remove the one here, I add it there. And well, that's not an eigenstate, but I can look at the space that is spanned by the action of all the powers of the Hamiltonian on this space. That will be an invariant subspace. And you can, in fact, do a variational calculation, and from what we see on the graph, you can exactly find the right behavior for small lambda. And in fact, we have a upper and lower bounds with the same coefficient for the quadratic contribution. So this is really the lowest excited state of this model, and something simple that is created by just playing with these root tiling and sort of modifying it somewhere. And things like this were done before or recently, and I think Frank Polman and his group are doing some interesting things where they look for eigenstates that are in fact higher up in the spectrum. Maybe energy is proportional to the size of the system, that are also obtained by inserting voids. At least that's, I mean, they mainly work numerically, but we can see we can construct exact eigenstates that have these kind of places where the tilings are messed up. They are not an allowed ground state tiling, and there's a finite energy, but they are actually compactly supported. And if you have a large chain, you can repeat that over many places, and you can make as high an energy as you want. And they are exact eigenstates of this Hamiltonian. And of course, they are low complexity as well, because of the way they are constructed. What's the time here? Okay. I should come to my conclusion. Well, there's some interesting things to discuss, I think. But first of all, this was just this one Haldane model for the 1/3 filled lowest lambda level, and there's many others. I think there's similar results we should expect for many of these other models, and I think that would be interesting to investigate. So people certainly have ideas about what you should find and when it should be kept and when not, and things like that. I think that would be interesting. Then there's, of course, the question, what happens if you don't truncate and you add these small terms without in principle of arbitrarily long range, even now it decays exponentially. So they are of the form, they are similar dipole preserving hoppings, but over longer distances. And I don't have to explain exactly what this term is. There is some coefficient that becomes small, and but in principle, all distances are represented. Right? And well, you could say if these are small, then we have this frustration-free model. So if we have LTQO, we will have stability of the gap. But of course, that doesn't quite work. We don't have LTQO. It's not possible. I think that there is some generic stability result that applies to this model. On the other hand, it's very much expected that this full model is also gapped, and so the race is on. So who will prove it? And will it be by some kind of understanding the stability, or maybe by some other method? I don't know. Another interesting point is these excited states. You know, so why not? It looks like that there might well be an entire basis of eigenstates of the spectrum of this Hamiltonian, which is highly degenerate. But if you choose the basis correctly, you can build it up with very low complexity states. Small Schmidt rank is what I mean by this. And so you can actually sort of understand the whole spectrum of this many-body system. It's not integrable as far as we know. There's no Leons or anything. There's sort of another way that it's a well-organized spectrum with states that can be described by these variations of fragmented MPS states. And sort of a last point I put. So if you're thinking about like some of us have, I think, what could we possibly prove, and what would be a provable statement, a mathematical statement, sort of expressing eigenvector thermalization hypothesis, that if you take a high energy state or the high energy, the high density of energy, it really should be the canonical Gibbs state if you look at local expectations. And thermalization in general is, I think, an interesting topic, but you have to be careful. So there are these obstacles here, these low complexity states, these highly degenerate, highly excited states that would definitely not conform with ETH. And so what does that mean for sort of the general or generic statement that you would want to prove? I think my time's up, so I'll stop here and be very happy to take questions.
Yeah, thanks a lot, Bruno. This was a great talk, and a perfect counterbalance to the talk of Stephen White of 2 weeks ago, where you kind of demonstrated that tensor networks also have some very nice theory underlying it. So I'm sure there are some questions.
Maybe I start with one. Like now this is for mu equals to 1/3, but for like in principle, could one expect similar behavior at other filling fractions, like 1/5 if we just include longer range interactions, for example?
Well, I don't see why not, but it's not. We don't have to. I have spent no time on it, so I don't know. But there are similarities in the structure of these Hamiltonians. I mean, people have looked at these Haldane pseudopotential models from many angles for quite some time, and Duncan has been going around harassing people, and including Simone and myself, but the other mathematical physicists, if they're willing to listen, because all of these have an extremely rich structure. Mm-hmm. And what exactly it is, okay, I don't know. I haven't studied them, but I think one can bet that there is interesting structure to be discovered and exploited there, and it may well be actually some generalization of what we found here in the nu equal 1/3 case. I mean, that would certainly be my guess.
Okay, thank you.
But we don't have results at this point.
Thank you.
Actually, if I may add a comment.
Of course, Simone.
From what I understand, the story is actually all of these Haldane pseudopotentials are expected to be gapped. Above
but I guess except for the nu equal 1/2, you're right.
No. I mean okay, but the gap is always in these Hamiltonians from kind of the absolute ground state, which you can choose 0 and be to the next excited state. That doesn't mean that, for example, if you take this Hamiltonian, which Bruno discussed at the moment, and you go to half filling, where the ground state at this half filling will not be at 0. And you then ask, constrained to be half filling, what is the next excited state? Is there a gap above this state? Then the answer will be no for a half filling. I mean, not that anybody can prove this, but I guess any reasonable person would believe this, because I mean, this is what Emil, I mean, I guess Frank, you would immediately agree that this problem could be mapped to the XY model.
The numerical 1/2.
Right. If we sort of go to this Hamiltonian and go to half filling, then of course the ground state will not be at 0, but it will be at some positive energy. And then if I ask, constrained to this filling factor, what's the next excited state? What's the gap to the next excited state?
Right.
My understanding is that this gap, of course, will vanish.
There's certainly gapless.
Yes.
Part in it, yeah.
Yeah. But all of these Haldane models from the kernel, kind of from 0 to the next excited state, irrespective of filling, as far as I understand, they're all gapped. Also, the bosonic model is gapped.
So yeah, so I mean, yeah, he's explained me a whole range. I'm not sure we agree on numerical 1/2, but for the other fractions, he's certainly convinced that his models, that they are all gapped, and it would definitely be interesting to investigate it, especially if it is true that up to some small approximation, you can understand the structure of both the ground states and the excited states as having this fragmented matrix product structure. I think that would be quite interesting, and it would make it also possible to analyze it. Yeah, it's an interesting challenge. I hope somebody will look at it.
So if I may ask a question, so you can, if you would have now 2 of these quasi-particle excitations, would they form bound states? Would they, or would they form scattering states? Is there anything understood there?
Well, so we haven't quite gotten to the exact excited state. So, but some of these excited states that I showed, so maybe I should go back to. Well, no, I can explain it like this. So there are definitely excited states that are strictly finitely supported, right? And so they're stationary, and so they are exactly degenerate also for that reason, because you can translate them. But even if they are not finitely supported, so what we have understood, like for instance this magnetoroton state, you can also translate it infinitely many times if you have infinite space, and they will all be mutually orthogonal and exactly the same energy. So this is a little bit strange. So there's, in this sense, probably no interesting scattering. There is an absolutely flat band. So they're all flat bands, which is kind of unusual. It's not what you expect. The Hamiltonian, on the other hand, doesn't look that unusual. It's just a finite range interaction. Now, what happens when they start to interfere, they will certainly reorganize, from a new pattern with a new energy. Whether we should think of these as bound states or I don't know, but there probably are combinations of excitations that are again higher energy, supported by a slightly larger volume, but still of the same type. So not sure there's interesting scattering in these models. I don't know. Maybe people who have done lots of numerical calculations, which I haven't, maybe like Frank and the people he's working with, maybe they know something more about that.
Actually, we have a second question. So at the end of your talk, you alluded to the fact that it's very complicated to prove the stability if you start perturbing this Hamiltonian. So I understood that in systems like the AKLT model, people like Jarotsky, they have proven actually the stability of the gap, that if you perturb something like the AKLT model, that the gap does not close. So what is the obstruction such that you cannot prove this for these new for this new class of states for which you actually also have matrix product states?
Well, you're quite right. So the first result that applied to the AKLT model, for instance, the spin 1 chain, was by Jarotsky. But in fact, now we have a quite general theorem by Mikalakis and Zwolak. So this is the generalization of what Bravi, Hastings, Mikalakis, and Bravi, Hastings did to the case where the non-commuting Hamiltonians, right? And so the main condition, so we have a frustration-free model with local gap, but there is the LTQO condition that they call local topological quantum order, which is basically the indistinguishability locally of the different ground states you have. And that, of course, is not satisfied in this model. For instance, you can look at, how many particles you have in this interval and so on, and you will define many distinctions, right? Now, of course, you can generalize this stability theorem even further and allow for certain distinctions to be detectable and still prove something. For instance, there could be symmetry breaking. The discrete symmetry could be broken. That would not destroy the stability of the gap in the discrete symmetry broken phases. I mean, you certainly expect it, and in fact, you can prove a version of the stability theorem that covers that. But for this model, where the ground state that generally is that large and is combinatorial, LTQ is not satisfied. You can select locally a certain ground state you want by local operations. And that is, so general stability for arbitrary small modifications of your interactions is not going to hold. But it's an interesting question, of course. I mean, since from the physical point of view, we all believe we are studying the same type of excitations and the same gap that you would find in the full model, which is a Hamiltonian that in the sense of these small perturbations is close to it. But we don't know how to analyze it. And certainly, I mean, it's also clear, I mean, if you don't do this kind of semi-sophisticated stability arguments using Hastings evolution and so on, you want to do perturbation theory, it will not work. It just will not work. You can see that already in the numerics that there you have problems with the boundary excitations, and these large degeneracies are a real headache. So it's not a perturbative situation. And on top of everything, in the physical model, the coupling constant kappa has to diverge as lambda goes to 0, which is makes it even crazier. So we would like to be able to say that there is stability of a sort, that what we find in this model that we can analyze in detail is the same as what you find in the model that we at first derived physically, what the model Haldane came up with. And it is a stability question, but it cannot be addressed by anything that people have done so far as I know. I don't see. I don't know. Does that answer your question, Frank?
Sure. Are there further questions or comments? So maybe this is a good time for thanking Bruno for taking the time and giving this great talk. So we will put this talk on YouTube. We will send all of you a link, and we hope very much to see you back in 2 weeks. We will certainly send very soon an email with the details about this. So we are very happy that, again, you were so numerous, and we thank very much everybody to be here at such a late time in the evening. So Bruno, thanks a lot again, and we wish you all the best there in this strange land where you're living now.
All right. Well, thank you. And thank you all. Bye-bye.